You may recall back in Module 1, we created a regression line, the line of best fit between two quantitative variables. Now we're to the point where we can talk about the inference of that line. And we're going to talk more specifically about confidence intervals for the slope of that regression line. Recall that we did scatter plots. We had an example where we investigated the effect of studying on GPA. And so here it was the data set that we looked at, and we found the regression equation to be 2.215 plus 0.0487 times the study time in hours. And we found that regression equation to be right here at 2.215 plus 0.0487 times the study hours. And we kind of stopped there. And if you may recall, we said that later on in the course, we would investigate inference about this line. And now we're to that point. So now you have a better understanding of how sampling error works and that our model is full of error. So remember that famous quote from George Box, all models are wrong, but some are useful. So we want to focus here on the slope of the line. So note that our slope was computed based on a sample from a larger population, right? That is, the scatter plot is just a sample of students from a greater population. So our line is attempting to model. So our actual population may have looked something like this. So the full population is more than just our sample, right? And the blue dots just happen to be our sample. So we can notate the true regression line. If we had the entire sample, we would get a slightly different regression line, right? And we can notate that with mu sub y equals alpha plus beta times x. Imagine this. Each sample that's taken, it's going to have its own regression line with a slightly different slope and y-intercept. So the notation can get a little tricky here. So let's look at this. So rather than using the familiar algebraic form of the equation of the line, y equals mx plus b, we've been using the y hat equals a plus bx. And sometimes we ventured and used y hat equals b naught plus b1 times x. So just remember this. Whatever the symbol, the coefficient of x is always the slope. So as you might expect, the sampling distribution of b, or b sub 1, the slope, is close to normal, with the mean slope very close to the population slope, and the standard deviation is going to be given as sigma sub b equals sigma over sigma sub x times the square root of n. And as usual, we don't actually know the population standard deviation, so we're going to use s, which gives us the following. So the standard error of b is s divided by s sub x times the square root of n minus 1. Now the AP exam actually gives a slightly different formula. So recall from the unit on regression in Module 1 that s is actually given by this crazy formula, the square root of the sum of y sub I minus y sub I hat squared divided by minus 2, all that divided by the square root of the sum of the x sub i's minus x sub r squared. In our formula, you can kind of see where the s comes from. From the top, we plug this in for the s, and that's where we get that. These denominators are actually the same. Just trust me on that. But as usual, we generally do not turn to these formulas. We will usually be using the TI-84 or StatCrunch or some other computer software to crunch out these confidence intervals for regression. So while I am going to build the interval for you to see where you can see where those parts come from, in practice we do not create these by hand. Often though, they will give you the output, and you need to be able to interpret that output and to create the interval based on that output. And we'll show you some examples of that here in a moment. First, let's look at the interval. So our slope is going to vary from sample to sample, and we can quantify this variability with the confidence interval. And it's constructed exactly the same manner that we have done earlier with the t-interval. The details of this can be found in the reading. So recall from the other confidence intervals that we've constructed, we have statistic plus or minus margin of error. What is our statistic here? With proportions, it was the p-hat, the sample proportion we obtained from our data. With means, it was x bar, the sample mean that was collected from our data. And in this case, it's going to be the slope. It's going to be b, which was used to estimate the population slope. So it's going to be b plus or minus the critical value, t star, times the standard error of b. And again, remember our true regression line, which we generally do not have, right? We're taking a sample and we're just estimating these. And here t star, the critical value for the t-distribution with the degrees of freedom of n minus 2. As usual, we're going to have some conditions that need to be met before we can proceed with our interval. So our first condition is that it's relatively linear, and we check this with the scatter plot and residual plot. And we've done this back in Module 1. Scatter's a scatter plot on the left and the residual plot on the right. And recall that we're kind of looking to see if it's more of a sort of a cloud of points that are above and below that y equals 0 line. Independence. Is there any reason to think that they are not independent? The nearly normal condition. So we're going to check with a normal probability plot or histogram of the residuals. And so there's a histogram of the residuals. And then there's the QQ plot in StatCrunch. The normal probability plot produces the same thing. We're looking for roughly linear around there. Little curvature there, but nothing to raise too big of an alarm. And equal variances. This may be something a little new. What we do is for all the values of x, we expect that the variances are about the same. What we would not want, so on this top, we've already plotted the residuals. We do this often with a residual plot. What we don't want is something like this, where it fans out, where it may start off with very little variability, but then we can see it fans out into greater variability. The variances need to be, or standard deviations need to be roughly equal as we proceed for each value of x. So that would be bad if you see a fan on the residual plot. Now often, particularly on the multiple choice type problems, it will say the conditions for inference were met. On free response questions, but you should indicate that these conditions are satisfied. So you should say, we've checked for linearity. This appears to be roughly linear or follow a linear pattern. We've checked residuals, and equal variances appear to be equal. We've checked the nearly normal condition where we've plotted histograms, and you may even want to sketch out some of these, a rough sketch. So let's go back to our example that we were looking at with GPA versus study time. So here was the computer output. They'll often give you problems to create confidence intervals by giving you the computer output and asking you to create the interval. So recall our interval is b plus or minus t star, the critical value, times the standard error of b. Now we actually have b and we have the standard error of b, but what we don't have is the t star. So let's look this up. You can look it up in the table. I'm going to show you on the calculator how to look that up. Again, we're going to look up df of n minus 2, and our sample size is 35, so our df is going to be, you guessed it, 33. And we're going to do a 95% confidence interval. It may be tempting to look at the t-stat, but this is not the critical value. This is the test statistic, and you'll look at this later when you do hypothesis testing. So to find the t-star, I'm going to inverse t, 95%, so the area is going to be 0.025, degree of freedom, 33. And we get a t-star of 2.0345. And we can carry that out a little bit further if you want. So plugging this in, let's go ahead and label our points. So the b is the slope, and we're given the slope here of about 0.048723. We're given the standard error of the slope. It's given in our table at 0.01772365. And we already found our critical value. So plug that into the formula. And I'm going to crunch out the part to the right of the plus minus to get my margin of error. So it's 0.048723 plus or minus 0.036059. We can express this as an interval by adding and subtracting that margin of error. So our interval is going to be 0.012664, comma 0.084782. And remember what we just found? We found the 95% confidence interval for our slope of the regression line. So what does this mean? We are 95% confident the interval from 0.0, I'm going to round to 3 places here, or 4 places, 0.0127 to 0.0848 captures the slope of the true regression line relating GPA, which was y, and study time x. So we can put this a little bit better context, I think. We can say we're 95% confident that each additional hour study time x is associated with between a 0.0127 and 0.0848 increase in GPA. So a couple different ways to interpret it.